Hello and welcome to the fourth in a series of 5 ventilator related videos. This video describes possibly the world's smallest and strongest DIY ventilator technology demonstrator, which employs an Ambu Bag or Bag Valve Mouth BVM ventilator device. But before we begin to look at the device, let me tell you a bit about the Ambu Bag or Bag Valve Mouth device. This is known as an Ambu Bag or Bag Valve Mouth device. It's a simple life-saving device. The mask is placed over the patient's face. The medic squeezes the bag by hand on typically a 5-second cycle. Air passes from the bag through the valve and the mouthpiece to the patient, and thus they are ventilated. However, these BVM devices need someone to be present to permanently provide the squeeze. The technology demonstrator I'm about to tell you about automatically and regularly squeezes the bag to provide air to the hypothetical patient. The volume of air supplied is important. It's known as the tidal volume. A small amount of air for children and a large amount of air for adults. The technology demonstrator provides an intuitive control for the tidal volume. Finally, the frequency of squeezing is important. Usually less frequent for adults and more frequent for children. Again, the technology demonstrator has a speed control function. Let me give you some more details. The technology demonstrator is a simple design comprising 7 short pieces of timber, 1 pivot, a few elastic bands, a plastic bottle and an Ambu Bag or BVM device. Control is achieved with an Arduino microprocessor, although it could equally have been a Raspberry Pi microcomputer, another microcontroller, or even some simple bespoke electronics. A relay controls a pneumatic valve, originally designed to be employed with a pneumatic cylinder, inflating the plastic bottle with compressed air and forcing it to deflate under pressure drives the BVM cycle. The Arduino program controlling this has less than 200 lines of code, and the demonstrator is fed by a 12-volt DC supply and a compressed air source. Okay, now let's take a quick look at the device. Quick things to note: it's small, compact, tidy, uncomplicated. Only one line feeds in, and there would be one line feeding out to the hypothetical patient, but we haven't got an extension for the face mask at the moment from Ambu. It's got a handle. It's easy to carry, it stands on its own, it's robust, it can work this way up, or this way up, or this way up, or even this way up. Notice the hinge here. Not a sliding action, nor a pressure vessel, nor a rotary motion, all much harder to engineer and manage. Just a hinge. 3 holes, a threaded bar and a few appropriate fixings. Easy. The plastic bottle is employed as the albeit unusual pneumatic cylinder that drives the machine. When air enters the bottle, it lifts the semi-seesaw arm and squashes the Ambu Bag, squeezing the air out into the face mask and the patient. When the air supply is turned off, the arm is pulled down by elastic here, and the cycle repeats. Now let's go through that in more detail. We'll start with the main machine, but let's first turn it on. The chassis is composed of 7 timbers, a base timber, 4 identical uprights, each screwed in with 2 screws at the bottom, a hinging beam and a static top beam. Note, all the timbers have round edges to minimise the damage to other fittings. The hinged arm is readily produced. It's much easier to make than a sliding mechanism, fabricated pressure vessel, or employing a windscreen wiper motor, as seen in many other simple ventilator designs. The threaded bar, screwed rod, of which there are 3, 2 act to bolt in place the top beam, which is adjustable, and the third acts as the hinge for the middle beam. The bottle is 100% as it was manufactured. No modifications are required. This is a 1 litre bottle and it was chosen because it lacks the rings around the middle, seen in many bottles, which I believe enhances the bottle lifetime. Elastic bands are used to hold the bottle in place. We didn't originally have those there, these are a new feature, and to make it even more positionally secure we could put little notches in the top edge of the beam to prevent the elastic band walking up and down, which we've never seen. The cap has a single hole that's approximately 0.5 millimetre under the outside diameter of the air line that goes through it. The air line, let's just stop it for a moment. Notice that a red light comes on indicating that we've stopped the machine. The air line passes through the cap in a rather clever way, and there are 3 things to note here. 1, there's a chamfer on this folded back airline, and that means that the load of the airline pulling out is very close to the airline itself, so it doesn't tend to twist. 2, the airline is held folded back by a number of elastic bands. And 3, there's a hole cut in the end of the airline so that air can escape into the bottle, otherwise the airline would be sealed by the fold. Very pragmatic, it's caused no problems whatsoever in operation. The Ambu Bag is located on its handle, and again a few elastic bands are used to help ensure it remains in place. On the end there is an elastic return which forces the hinged arm down and squeezes the air from the bottle before the next cycle. There's a handle on the top, but it could be repositioned because it does get in the way of the Ambu Bag positioning. Note, there's currently no upper or lower stops on this hinged arm. Stops could be put in place here to better manage the tidal volume of the Ambu Bag. Okay, that's the machine explained. Now let's look at the control system, microprocessor, relay and pneumatic valve. This is the microprocessor. It's an Arduino Mega. It could have been an Arduino Uno or indeed one of many other from the Arduino range, or a Raspberry Pi. There are less than 200 lines of primitively written code controlling the system. Another alternative would be a microprocessor 555 timer instead of a microprocessor. The relay board, we're simply using one relay to drive the machine. We've got a spare relay being set at the same time, just in case one relay should fail. Not that I've ever had that happen, but there they do. And we're using the other 6 relays as information to the operator for increasing the frequency and reducing the frequency of the machine. So let's just increase the frequency of the machine. If we plug this around that port there, oh, sorry, we're decreasing the frequency here, so now the machine should slow down slowly at about a tenth of a second. I did add it to the cycle time per cycle. If we wanted to increase the speed of the machine, we just ground a different pin. The LED here indicates that the frequency is being increased. Here we have a pneumatic valve designed for a hydraulic cylinder. We're using one outlet and we've sealed the other outlet. In, we've got 12 volts DC coming from a transformer and about 1.5 bar coming from a compressor. Note that the wiring layout here is very vulnerable to damage And I've laid it out like this simply. Let's not speed it up anymore now. That will slow it down a little bit. So now decreasing the speed again. That wiring is very vulnerable, really though. That should be packaged in an appropriate container. Now let's take a quick look at changing the tidal volume. To reduce the tidal volume, we can move the BVM device to the left, back along the half seesaw arm to where it's squeezed less. To increase the tidal volume, we can move the BVM device to the right, where the hinged arm moves more, and so the BVM device is squeezed more. The flexibility of the design allows other adjustments too. The hinge height can be changed to suit different sized plastic bottles. The top beam can be raised or lowered to accommodate smaller or larger plastic bottles and BVM devices, and the plastic bottle can be moved to the left and right to facilitate yet more control over the tidal volume. Moving the plastic bottle to the left increases the sweep of the hinged arm, and so increases the tidal volume displaced by the BVM device. Moving the plastic bottle to the right reduces the sweep of the hinged arm, and so reduces the tidal volume displaced by the BVM device. And finally, this is a very simple Ambu Bag Valve Mask squeezing device. It's trivial to make and is tolerant of poor manufacturing processes. It's strong and there's little to go wrong, jam or break. It offers both tidal volume and frequency control. The condition of the bottle requires monitoring. However, the bottle used has seen many hours of operation, frequently been overpressured, and continues to function perfectly. And bottles are very widely available. If you choose to develop this design or take elements from it, I'd be pleased to hear about your technology demonstrator. But please do read the disclaimer. Thanks very much for watching. Andy Firth, goodbye.
Bye.